Hello, everyone. Welcome to our rootlabs session today. Today we are joined by our two guests, Paul and Joeri from Mediahuis. Today they will talk about their data setup at Mediahuis, about why they chose Dask as the key component in the setup, while data roots usually like using Spark. We're also joined by Tim and Nicolas. Tim is a data architect at Dataroots. Nicolas, a data engineer, DevOps engineer at Dataroots. They have a little bit more experience with Dask than myself, so they will probably have more meaningful questions than I will have today. So, without further ado, I give the word to Paul. And yeah, Paul, the floor is yours.
Okay. Just see if the presentation works. Yep. So you should be seeing my screen by now. So the question that came to us was, why did you choose for Dask and not Spark? So we try to give you an answer to that in the next couple of slides. We'll start off with the Mediahuis and the data team. So what is Mediahuis, the company? And go on with the drivers of our architecture. Then we'll go on to the high-level architecture, together with a couple of the components. So Glamour is our data science platform, Dask, the distributed engine, the scheduler on next to it. And then I'll also, we'll dive into a couple of the components like the catalog, data hub. It's our hub for data, and I'll dive into the responsibilities of each player. So what is Mediahuis? It's a newspaper and magazine publisher in Belgium, the Netherlands, Ireland, and Luxembourg. A couple of our brands there. So for Belgium, that's Gazette van Antwerpen, Nieuwsblad, etc. But we also have a couple of Irish, Luxembourg newspapers, and Dutch also. In Mediahuis group, we're at group level. We have a department, a technology and product studio, with a couple of domains. One of them is the data domain. For that domain, I'm the architect. And then a couple of personal photos there. That's my family. I have three daughters. Below that is my bike, one of my bikes. I'm pretty green in mobility. I try to be green in mobility. And one thing I'm particularly proud of also, I'm co-founder of a hackerspace or a maker lab, Area 3001. Joeri, next up.
Yes, so within the data domain, we have a couple of teams, a few data warehousing and BI teams, and a big data team. I'm a data engineer within the big data team and also the architect of the team. I have a girlfriend, but unlike Paul, I don't have kids yet. In my spare time, I like to go running with or without obstacles, and I'm also very interested in wristwatches.
Okay, sorry, I have to go on to the next slide. Yep. So let's go on with the drivers of the architecture. So talking about drivers, we wanted certain things when we set out to grow the architecture a little bit. We had some of it already. And what was it exactly? We wanted to have a data science team where when you add a new member to the team, he could hit the ground running. What does that mean? Especially is like from day one, you want to have a platform available. You don't want him to set up drivers, have different versions of drivers. The libraries don't match with the database, etc. One of them wants to work with Linux, the other one with whatever. So we don't want that. We don't want to have them to build up the engineering or system knowledge. So it used to be that they needed to know where the data resided. So they had to know, like, okay, the views are in the Oracle database here and there, and we don't want any of that. Just want to hit the ground running. So also that means that if you have a team, you want them, some of that knowledge of the domain is already acquired and implicitly in notebooks. You want them to be able to share those instantly with other members of their team. Also the data that comes out of those notebooks, etc. So you want your platform to be to enable that kind of sharing. Then hiring and industry standards. When you want to hire in Belgium, especially, there's certain number of things to keep in mind, especially for data scientists. There are not so many, there were fewer, I think. So that was an important goal. Fast to production for reports, models, and dashboard. That means once your data scientist delivers something, you want to take that time and put it into production as fast as possible, being it report or a model or whatever. It's just the exploratory to the production phase. You want that to be extremely fast. The data engineers, most of the drivers there was like to be really focused on the customer, being the data science team and analyst, of course. And you want to do that with a small team, and that means also that you want to productionize it with as little errors, extra errors, and as little time wasted as possible. I'm going to go into the first three as one block. So no setup drivers, libraries, no engineering system knowledge, no knowledge sharing. We need knowledge sharing. So how do we do that? We have like Alice is our persona for the data scientist. You want to give her a laptop first day, and she just needs to have a URL to go to the Glamour platform. Glamour is our data science platform, and Glamour has a couple of functionalities that you can put or link Alice to a certain team. She will have a team folder, etc. So you want that knowledge sharing to be in that platform. And then when she connects to the data sources, and we'll go into the data hub and what it means later on, but there are a number of data sources in a data hub. It's just a concept. And we abstract that away from her with the introduction of a catalog. And so she just needs to know the catalog and the data types there, and then she'll have no view, or it's not necessary to know exactly where that data resides, and she'll get one interface. So that's for the drivers, the first few, and then for the other ones, so the hiring and industry standards, fast to production, and the production without errors and time wasted. First, I'd like to clearly say what we mean with fast. So when the question first came for like, why did you choose Dask and not Spark? It kind of gave a hint like, can you indicate the performance differences? And we see those blog posts also, but we're, as a company, not so much interested in that part of the equation. For us, fast is Alice and Eugene, our engineer persona. They need to work together, yes, and fast means Alice has some business requirement, some idea that she wants to test, and fast is putting it into production from the beginning to the end. That's fast for us. So if we tie into the other drivers there, like making Alice her development fast means industry standards like scikit-learn, Python, typical, very fast to develop in. Pandas is ETL2 that 4 years ago when we made these decisions, it was on the rise already. And then we have like more or less the options from Alice to Eugene. We need to move code over from one team to the other. We can do a Dask, and Dask was 4 years ago like almost production worthy, I would say, and or Spark was more reliable and more mature. So we have the options there. If we compare them a little bit, you could make them work with like PySpark or something, and then you see that a big difference is that in Spark there's an optimizer, and so you would kind of rely on that optimization as an Alice or Eugene 2. You don't really know what he's doing with your data sets, so it's kind of auto optimization. And then when you compare that to above, where Alice would work into in Dask and Eugene 2, there's more of this encompassing view on optimization. So optimization for us does not only mean, and you cannot compare it like Dask has no optimizer, Spark has an or little optimization, Spark has a bigger optimizer. The optimization for us is the whole encompassing box. Like, do you really need to do this kind of calculation? Can you do it on a subset? That's not something that optimization in a Spark optimizer typically includes. You can really work in a different trajectory, a different path of your data science to do the same work when you know, for instance, that a job is difficult to perform on a cluster. And for that, you typically need domain knowledge, which Eugene is not required to have. Like, you cannot rely on the data engineer to do that kind of, it needs to go into the discussion with Alice. So there's two different approaches, or you optimize it based on just the code that you optimize, and you don't ask questions on what you're doing. And for us, we more or less see like, okay, optimization is the complete thing. You need domain knowledge for it, and you optimize, you give Alice feedback so that she can optimize it herself. So Dask would need to give good visual feedback on what's going on into the cluster so that Alice can tune or change the whole setup of her analysis to be able to work on the cluster more efficiently. And then we saw that Dask indeed goes into that, trajectory and like gives a very good number of visuals. I think Joeri will go into detail, so I'm skipping the details here, but it gives you like on a logical level and on a physical level what exactly is happening. And it's not like in Spark, you go to an IST and then optimize from there. It takes a little bit of time, a couple of seconds most of the time, and on a minimum. With Dask, it's more like a millisecond basis, and you get it. It's more interactive. So performing from a notebook, you get these kind of visuals. So we compare that, we think that Spark gives more or less the same data or insights, but it's presented maybe a little bit different. I must say I'm not a Spark expert. I've worked with Spark, but it's been a couple of years, and it might have evolved a little bit or more. I don't know, but I haven't seen it yet. So please correct or send in comments on approaches there. What else gave some weight is that Python is quite is more popular overall than, for instance, Scala, or we had more access to data sources. It's easier to debug in a single thread. You can so Dask is made on distributed, and you can also put it into a single thread mode, which makes it easier to debug. Sometimes when we made our first catalog library ourselves, it was very nice to have like a single thread that you can just debug through. There's nowadays, it wasn't like that, but nowadays there's Rapids from NVIDIA, which allows for GPU, and those are also more mature. Didn't tie into the equation like 4 years ago, but just mention it here. We have a lot of more visualization libraries in Pandas available. I'm guessing, I'm pretty sure, but not 100% sure. I don't want to offend anybody with Spark knowledge, so disclaimers. It's easier for the deep learning, I think, also. Manual optimization, of course. What's good about the Spark approach, I think, is the auto optimizer. It's much less risky, and you have much more support for consultancy, etc. The streaming solution was way more mature then. I looked into the code of the Dask streaming solution, and there were a number of things you would typically expect that were missing still. That can be changed, I have no idea. And the SQL engine is much more mature, although that nowadays we also have like Dask SQL, which I think a number of players on the market are investing heavily on, and we're also looking into that too. So I think Joeri will take it from here with the high-level overview.
We have one question from the audience as well.
Sure.
Ahmed asks, could we do extra optimization on top of Spark automatic optimization?
Yes. Although I think that the you can, of course, yes, but the way that Spark gives you feedback as a data scientist with the different stages and the fact that it's not very responsive like cell per cell. When you execute it cell per cell, it takes like milliseconds for Dask to put it back into the visual and into the dashboard, and like really see real time what's happening into the cluster with the shuffling of the data, etc., even which nodes are sending data to which other nodes. And that kind of interactivity we think it's necessary for the data scientists to really have the maximum of the feedback. Otherwise, they will start putting a lot of computations in one cell and then execute it. And that's also where I think, since they're both lazy, but the optimization of the AST shines more for Spark, since it takes your complete code what you want and then optimizes all over the place. And that's the use case, I think, also, while we're more like, almost rule per or line per line optimization. Okay, now it's doing this, and this is a difficult step for the Dask engine. So let's try to change it there. I think it's the way of working. I'm not saying that it's not possible. It's sure possible, but it lends itself a little bit less for the interactive way of working.
All right, thanks for clearing that up. Another one from Gauthier. Did you consider other options than Spark and properly Dask?
I think not so much. No, that was more or less, we're pretty open source, or I'm personally pretty open source minded. No, not really so much.
All right. Yeah, then Joeri, I won't interrupt anymore. Go ahead.
Oh yeah, I'll. Can you do it, or are you doing the slides now, Joeri?
I'll take over. Yes.
Okay, cool.
Oh, whoops. Okay. Slides should be visible now. Oh, we went all the way back to the beginning. So a quick overview of the Glamour Platform, which is the nickname for our data science platform at Mediahuis. At the top left, we can have Alice, the data scientist. And as Paul said before, Alice just needs a laptop. Technically, Alice could even use Glamour on her smartphone, even though it's not really recommended because it's very difficult to program on it. Within Glamour, every of our users gets their own Jupyter environment. It comes with a pre-built image that we as the data engineers maintain, which contains, well, whatever package they need. Most of the time, our current image contains Pandas, scikit-learn, Intake, which we use for the catalogs, well, Python, of course. Dask, we're currently working with Panel as well for dashboarding. If anything else is needed for the data scientists, we as the engineers will take care of it, that it lands in the image. And then if one of the notebooks actually need to be run on a regular schedule, we have Airflow as a scheduler, which we can use to run the notebooks. Within the Jupyter environment, Alice will make use of the catalogs to access data in the Data Hub. Data Hub is a concept of all the data that's available throughout the company. All the data that's available for, let's say, data purposes, not the data stores that are used for the actual applications, so that we don't want to risk a data scientist being too eager with a huge query and taking down something that's crucial for the newspaper. So the Data Hub contains data specifically for data purposes. The biggest data in the Data Hub is from what we call Glitter, which is the tracker we use on the websites and the applications. Because it's the biggest data source, it's also still the main use case of Glamour, because there are no other tools within the company that people can use to work with that huge amount of data. On top of the Data Hub, we also are currently building a metadata catalog for which we're using Amundsen, in which Alice can then see like what is the recency of the data, who is the producer of this data set, all those kind of things. Moreover, the data scientists from the Glamour environment will also put their own data into the Data Hub. And on top of the Data Hub, we then have a small data API, which can be used to retrieve certain data sets. So to give a very concrete example, if a data scientist is busy building reader segments based on the reading data, they can be stored in the Data Hub, and then people can do a call to the data API if they have the right authentication, of course, with a user ID, and just retrieve all the reader groups of that reader. Then what happens within the Glamour platform? It's built on the Kubernetes cluster. So in this case, we have two data scientists, Alice and Bob. Alice and Bob need a GitHub account for authentication. And then using Jupyter Hub, they each get their own Jupyter environment with the image that we as the engineers provide. One of the features here is that also the data scientists can install as many packages as they want. If they completely mess up the environment, they just need to shut down their server and start it up again, and then everything will work because they will start again from the default image. Separately from the image, of course, they have possibilities of storing data and storing their notebooks, which of course persists throughout restarts. And in the past 2 years, we've only had one person, one time, who managed to really break their environment to the point that a simple restart was not enough. So it works pretty solidly. Then, of course, in the Jupyter environment, you have Jupyter notebooks, and in each notebook, we have a simple utility function that the data scientists can use to start a Dask scheduler. And the Dask scheduler is the component that does all the communication with the cluster, the Dask workers, which data scientists in our environment can just spin up when they need them. They get the same images installed on them. And yeah, in essence, you can scale to the moon and back as a data scientist. Then let's get into what Dask actually is. Going to switch tabs to go to a demo. On the left, we have Pandas, and on the right, we have Dask. So going to, wait, I have to go back to my presentation. I was too fast. First, an overview of what Dask is actually. I'm assuming most of you know what Pandas is, but it's used to process data frames in main memory. And it's typically used for Excel files or slightly bigger than what you can handle in Excel, but still it's limited by what your local machine can do. Back when I used to do a lot of data science work in Pandas, I had a MacBook, and I saw this thing like on a weekly basis at least, most of the time, a couple times a day. And of course, every time you get a warning, but before you can reach the force quit button, your entire thing has frozen, and yeah, you have to restart. So Dask to the rescue. In a nutshell, Dask is distributed pandas. It's suited for really big data, and it does that by orchestrating a number of smaller pandas data frames, which it then scatters across virtual machines, how many virtual machines you have. And a Dask data frame is in essence a graph of functions across smaller pandas data frames, which are spread throughout your cluster. Okay, now I go to my demo. So on the left, I'm using a simple taxi trips dataset, which is very popular in data science. I have to restart my kernel. It happens every now and then. So I'm reading the taxi data and then trying to get the first few rows from the data. Yes, it's restarting. And on the right, I'm doing the same thing with Dask. Not doing the same thing with Dask because I changed the path. Yes, I'm getting the head. Still using the wrong file. It should be there. Okay, my apologies then. It's no live demo. Luckily, I prepared for exactly this case, and I have screenshots. So on the left, we have pandas. We take the first few rows of the data set. We can get the shape or description of the data frame. And on the right, we're doing the same thing with Dask, which, of course, you'll see is extremely similar in syntax. The first difference you notice is on the second line. On the Dask side, we're using assume missing. This is because, of course, Pandas will read the entire CSV file into memory before it does type inference. Dask will just, because it's suited for big data, it will just read a few lines. And if those few lines are just integers, then maybe later on there are floats or not the numbers in the column. So here we tell Dask to just assume that if there are integers, some of them might be missing. So cast it as a float. We take the head, which is exactly the same in Dask as in Pandas. Then if we take the shape of the data frame, we see the first difference. Dask uses lazy execution. So at this point, we have delayed, which is a function which will be executed when it's necessary to get the number of rows in the data frame. The metadata will tell Dask that there are 11 columns, but we don't know how many rows there are until we really need it. To tell Dask that we really need it, we use .compute, and then you can see that we get the exact same result as in Pandas, of course. Similar with the describe, again, you have to do a compute to get your results. And then you can visualize what it actually looks like, the Dask data frame. So as I said, it's a graph. It uses the pandas functions underneath. At the bottom, you see pandas read text. And then it has a separate compute graph for each of the things we get in this description, which is count, mean, standard deviation, and so on. So you can actually investigate this visualization to see what exactly is going on underneath the hood. Of course, the main power of Dask is when you use it for a distributed setting. So in this case, we're spinning up the workers. As I said, we have a simple utility function, which is setup worker Dask. And then you get the cluster widget, which you can use to tell us how many clusters you want. And then our auto-scaling Kubernetes cluster will spin up those workers with the right image. To showcase this, I'm reading a bit of a larger version of the taxis dataset. I duplicated it a couple of times. Because it's on a data lake, we also have to provide direct credentials. But other than that, we're doing the same thing as before. And now if we compute the shape, you can see that we have 13 million rows, and they are split across 36 partitions. Each of those partitions is then a Pandas data frame. A brief intermezzo to talk about the catalogs. So all of our data available in the data hub at Mediahuis is available in Glamour through a catalog system. So everybody will have one big catalog, which is called the master catalog, which has a bunch of subcatalogs, and those subcatalogs then have all the data frames, so that our users don't have to bother with the details of how the data is stored and where it is stored. So for example, the earlier taxi data set, we could put it in the catalog. We do it once as the engineering team, and then all of the users can just use it as catalog.taxisbig. And yeah, they don't have to bother with details like the assume missing or anything. All of that is handled on the engineering side. And moreover, if as the engineering side, we decide, okay, we're moving our data maybe away from the data lake to an S3 storage, we can again just edit this on the catalog level. And for the users, nothing changes about this. Which also helps a great deal in what Paul said before, into getting data scientists up and running as quickly as possible. They don't have to go ahead and discover where all the data is stored. It's all there in the catalog. Back to Dask, one of the very useful visualizations in Dask is the Dask Graph. This one here is to compute the length of a data frame, the number of rows. So you see here again the 36 partitions that are coming back from earlier. So Dask does a few actions to read in every partition and compute the length of every partition and then aggregate it. What this graph tells you is that this operation is very nicely distributed. If you get the Dask graph and it looks like a complete spider web with everything going everywhere, then you know I'm doing a lot of unnecessary shuffling. Or maybe in specific cases it actually is necessary, but then you know as a data scientist, like, okay, maybe I have to double check my code, maybe ask the engineering team to look at it. The partitions, so Dask has a function called map partitions, which you can use to do an operation on each of the data frames. Very simple here. I just asked the type and the length of each of the data frames. So you can see that actually those data frames are Pandas data frames. Dask did some automatic chunking on the CSV files that we were reading. So we had 9 files. Each file was divided into 4 partitions. And you can see here that the first 3 reached the maximum size, and then the 4th one is just whatever was left after splitting the first 3 partitions. But you can use your own knowledge of the data to repartition the data. For example, ask for partitions of size 500 megabytes. And then we get nicely divided partitions. Then again, if you see at the bottom line, if we ask for the partitions again, we still get 36. One important thing to know about Dask is that it never does anything in place. All of the Pandas functions that take an argument in place, this in place argument does not work for Dask. You need to really store it in the return value or it's gone forever. This has a lot to do with the fact that that the Dask data frame is a graph more than anything. Let's do an actual operation on the Dask data frame. So we're doing a group by of vendor ID on the data and doing some sums over the passenger count and the trip duration. On the left, we're doing it in Pandas. It operates very fast, 5 milliseconds. Of course, this is only, 70,000 rows. On the right, we're doing the same thing in Dask. Again, we need .compute to get an actual result. And then the first time we try to time it, you see, it takes 36 seconds on average. This is, of course, ridiculously long. But the issue here is that those 13 million lines scattered across 36 partitions, they have to be read from the disk, from the data lake. And that's what's taking so much time. So what we can do here is call persist, which will tell Dask, okay, take the data from disk and load it into the memory of the worker nodes. Do that once and then keep it there so that we don't have to do the overhead of reading the data at every operation. And then if we do the group by again, we see that we can do it on average in 230 milliseconds, which for being 13 million rows is quite impressive, I think. Some more of the visuals, you can get an overview of the workers you have available. You can see how much memory and how much CPU they're using, which is very useful because sometimes data scientist is trying something, it's crashing. So then we tell them, check the workers, check how much memory they're using when they're crashing. If you see that each one of them is using 11 gigabytes out of 12 before they crash, you're probably going to have to use more workers because the memory load is too high. If they are on 2 gigabytes and they still crash, then something else is wrong. You could run this on 20 workers, it's still not going to work because that's not the issue. You can also get the compute time per task, per function in Dask. So here it's very small, but on the bottom left, you can see the big one here is from delayed, which is the function that is used to read the data from disk. So in our example, that was the main, the slowest part of the computation. A lot of reading text, then aggregating, and so on. You can use this to profile what you're doing. And then one more thing you can do with Dask. This is something that pops up in a lot of Dask tutorials, because you can use this even if you don't have an entire cluster set up with workers. You can still use it to schedule your functions. Schedule in like a multi-threading way. So here I made a function that reads one file and returns the length of the file. And you can submit a bunch of those functions to your cluster. And then if you have workers, they will get executed. Those functions will get executed across the workers. But otherwise, you can also run it locally and it will still use them in a concurrent way. Then the final step is that we also put these notebooks into production. Also, as Paul said, to get things into production really, really fast. We have a small YAML description of the jobs. This is for a churn example. You see it's very simple. It just says when it has to be executed. You get some parameters. So back. Some parameters to the notebooks, and then you say what notebook it is. Together with the notebook, that goes into a Git repository. for which we have an automatic pipeline that puts it on the data lake. And then our scheduler will read the information from that data lake and will know when the notebook has to be executed. This is also going to be executed on a Kubernetes container with the exact same image. So if it works in your Jupyter Hub environment, it will work when scheduled. To give you a quick example of how fast we can go to production. So last year when the lockdown happened, all of the news companies saw that they were getting a lot of new subscribers because people were really following the news. And of course, the people at sales, they had the immediate instinct to say, okay, we have new subscribers now. How can we keep them? So we needed a dashboard specifically for those new subscribers, for which we need a few new data sources, which we took care of on the engineering team. We had one data scientist working on it. And in 1 week, the prototype of the dashboard was in production. And then, without any effort from the engineering team, the data scientist improved it for 2 more weeks. So in 3 weeks, we had a fully performing dashboard without any big load on our data engineering team. Then maybe I will skip over the detailed overview of the scheduler and hand over back to Paul for final parts.
And in the meantime, we also received some questions from the audience again. The first one from Sumit Kumar Gupta. This means that Dask is more explainable than Spark? Question mark.
That's a very good question. I think it is because you have all the visualizations, you have the graph that you can really investigate. Now, of course, there's still a limit to how understandable all of that is. Sometimes it still boils down to a bunch of low-level mumbo jumbo that nobody will ever understand. But yeah, you can dig deep, and depending on your own skill level, you can understand to a certain depth. And I also think that, especially with the high-level visualizations, it's very understandable for data scientists. If they know Pandas, then it's quite explainable what's going on in Dask. How many workers? So these are, they are pods in Kubernetes. And well, it depends on the size that you make them. But in general, for simple things, it's about 4 workers. That's a sensible default that we always tell people, like, try it with 4 workers. If that's not enough, then make sure you know what you're doing. But some people use 15 for bigger jobs when you need to process like a month or 2 of data.
All right, thanks. And then I'll give the floor back to Paul.
Okay, then I have to skip on some slides, apparently. Could have done that. Sorry. So we would skip the scheduler, I'm guessing. Let's go on to the catalog. So one of the reasons why it's very important is that it abstracts away. It's been told 3 times, but it's very important. So what intake does is it reads the catalog, and what's in that YAML file is put in there by Eugene. And it's like the driver, for instance, is this CSV? Is this a Parquet driver to use, SQL engine, where it is, location, and how to parameterize it. And what intake does is intake is also a project by Anaconda, and it works together pretty neatly with Dask. And so if the data of Bob runs the notebook below without the Dask, intake will make sure that when you execute your read from your catalog library, that you will get back a Pandas data frame. So if you see up front on the top right corner there, customer DNA catalog dot DNA data frame, and you have to provide some parameters like which brand you want and an array of features that you want. I just ask for the best day, and I say read, and it gives me back a Pandas data frame. If you would execute similar code on the same notebook, but first ask for a Dask cluster, then the code will be the same, but you will get back a Dask data frame. Similar API. So again, it's part of our way of working where we say like Bob needs to know as little as possible, whether he's working in a local setup or going further than with bigger data sets. You should have as little work as possible, not reworking everything, but should be able to go from Pandas to the distributed version. And again, you see that there's an abstraction layer, and intake takes care of it. You just get a data frame. Whether Pandas or Dask, you don't need to know anything about the data hub, where it's stored, you don't need to know. So of course, maybe a small thing, most of our authorization is done on the SaaS providers of the data. So intake forwards the credentials to the Dask workers, and then they use that to get their piece of the data, which they load into their local memory or spill overflow on disk also. Great. And then let's go on to the data hub. Key things I want you to take away from here is that data hub is a concept, it's told before, but it's the concept of all of our systems that are used for, or their main functionality is used for storing and transporting data, not including the systems that also do stuff like that, but mainly with an application functionality. So for instance, the marketing automation platform, it has a lot of data. Yes, we could use it to read from. We don't do that because it has another functionality, and its main functionality is marketing automation, and its not main functionality is not data transport, etc. So Data Hub excludes those systems, and then we have two types of systems into the Data Hub: systems that take care of or are taken care of by providers like Azure Data Lake. You don't have to scale it, you don't have to do anything about it. And our own proper, for instance, data warehouses on-prem. Sometimes when we feel that it's better for Bob, for instance, to read from Azure Data Lake instead of the data warehouse. So what we often do is we export data in batch for data science purposes to a data lake, and we also use the data lake for staging for the data warehouse. We do a couple of ways of working. So basically 3 types of systems: the ones that can be used against exploratory loads, which you don't know when it's going to come and you don't know how big it's going to be; the ones that are more for operational use, like for reporting for Power BI; and then the ones that are outside of the Data Hub. And then I'm going to end with the responsibilities, 2 slides, one on the producers, one on the consumers. And producers, we work with the concept of a data steward, and how we like to understand it from Mediahuis is that data steward is the one that knows a lot about the data that's being produced, and we give him responsibilities, and those responsibilities are: you have to write the data on time onto a system in the Data Hub. And that means that we don't read on your system, you have to write it onto the Data Hub to be used by the rest of the organization. And what is on time, you have to add and update your metadata into a metadata catalog with a certain schedule. For instance, a daily 30 minutes offset from midnight. And that's your schedule. That means that the data engineer can write a notebook that tests whether your data is on time or not. And you can immediately have an alert. So the data steward is the one that receives the alert. That's also his responsibility to check whether he's the first in line, because he knows when his data, for what his data is needed and not. He has most domain knowledge about that. What else? In the metadata catalog, you can write tests. That means that, and we're still working on that part, by the way. We have a number of these tests in production yet, but for the meta catalog, they will be new. If you would say, like, I want this kind of distribution on that column or field in the data set, we can check it in the notebook. And then again, you will be alerted if the test failed. That means the data steward is the only one that knows and that follows up the news, etc., and can see, for instance, oh yeah, but that's normal. We had some military operation in the woods. It's normal that this data is not distributed, because he knows his domain most. Small part, lineage there. When data flows through your organization, you alert the one that's responsible for the data, but it also has an impact downstream. So we need to have lineage information in order to alert the downstream users that also their reports and might be hindered by missing data, or even worse, just wrong data. Well, so the platform is basically just provides the test runners against the metadata catalog. And then when you consume from the data hub, you also have what we call responsibilities. So you adhere to, you can just look up in the metadata catalog how this data is supposed to be formatted. And sometimes we used to see that a lot of teams, their first reaction is to ask data in a certain format and to ask the data team to provide something for them. And sometimes they even go directly to the other team, and we're turning that around in that we say, like, okay, but this is not part of the data hub. It's not part about transporting or storing data. This is part, it's mostly part of your application, because you're building this view for your application. So you need to take it up in like this view, and it's encapsulated in your, logically in your application. So for instance, we have a Kafka, you put your views on it. Somebody wants to have aggregated views of top performing articles. That's great, just to read the stream. Yes, build up your own view in KSQL-DB. I don't know what you prefer on that, but it's part of your responsibility, and it's part of your application. And only when we see a lot of applications, and we do see that, for instance, the example about our customer DNA is like a set of features that a lot of models use. Churn model uses it, etc. So these are things we know about our users and that we can leverage in a lot of our models. Those kinds of things we will store in the data hub, because we regard them as data products. So that's something that we sell, more or less, to our clients. And that would be too costly to build the same materialized view in a lot of different applications than we take it in as data engineers. I think I've reached the end of the slides. So I have a very nice question mark. We'll answer questions, means.
All right. Thank you for the presentation. So interesting. For me, it was very clear how you made this choice, at least. Yeah, I think Tim and Nico have some questions. In the meantime, we also received some questions from the audience. The first one from Hamid again. How do you create intake catalogs? Is this fully or semi-automated?
Joeri, go ahead.
Yes, for the moment, this is manual. We're looking, once the metadata catalog, the Amundsen tool, is fully set up, we're looking to make it at least semi-automated by extracting data from there. But at the moment, it's a manual job for the data engineering team. It's not a big job. It's quite easy to do, and we have it all in version control, but it's still manual.
All right, thanks.
Can I add to that the metadata catalog tool, it also will be automatically. So it scans the data sets available in the different tools. So we hope to achieve, to a large degree, a whole automation flow there. And the manual part will be the most difficult part, in fact, in the future. So adding stuff to it will be the most difficult part from an engineering point of view.
Yeah, well, in Spark, this is pretty easy to add stuff to the catalog, especially with Hive. So yeah, you can just say write to there, and you specify the table and or the database in the table, and you can just store it, and it's done. So it's fully automatic when you write to disk, for example. So that's, I think, a big difference between Spark or Dask, or just that feature is missing in Dask right now.
I think that I think it's correct. I'm sure it's correct what you say, but the scope of the metadata catalog involves mostly like reports.
I'm talking about the meta store here, but the catalog itself.
Yeah, two parts of the catalog. So the one used in Glamour will be auto-populated from the bigger one, and then the bigger one includes like reports, jobs, and not only like the ecosystem of the HDFS or stuff like that, but it will be a lot larger. We will add deployed models to it that we can see like, hey, this data set is missing. There's a deployed model that is in lineage using that data. So we needed a more encompassing view, and we looked at it, and the Amundsen, so the metadata catalog, will be largely populated also by Atlas, which is like ingesting a lot of data in our Azure ecosystem. And then we will, of course, use also like Google catalog to have the other cloud providers also give data to a layer of CSV files, which we then upload to Amundsen. That's we're still working on it, so we can come back and explain what we experienced there, because it won't be a smooth sailing, I'm guessing.
All right. Another question we got from Gautier: what do you use or plan on using for these data quality questions?
Joeri, or yeah?
At the moment, we have been looking into using Great Expectations as a library. So then we should be able to, on the metadata level, write a test suite for Great Expectations, and then get it automatically executed on the data to check for simple quality issues. That's what we're looking into, but it's not set up yet. Again, we can come back to give an explanation of all the walls we bumped against implementing that, probably.
We have some stuff also in schema P or something. There was something set up already for the streaming. So we did a couple of experiments, but yeah, I think Great Expectations is our best guess. We also experimented already with it, so.
Mm-hmm.
Yeah, right. Yeah, it's also what we're using quite a lot. Tim or Nico, any more questions?
Yeah, sure. I think to summarize, you're basically using Dask to run your ML or analytical pipelines, I guess. Your real data pipelines, you're using something else, or also Dask?
The Mediahuis is a history of or acquisitions of a lot of companies. So for this part, I can say yes. For the larger part, I must say we have 13 different schedulers, what we know of, and we did that count like 2 years ago. So we have SSCS, we have the custom schedulers written, etc. So but for this part, we use it running, for instance, feature engineering. Typical data engineering task is code typically written by data scientists that runs into production. So it's, in fact, the actual pipeline.
Okay. I see that, yeah, most of those, let's say, notebooks that are created are scheduled. Do you also use Dask for any real-time inference jobs?
When we, if I may, Joeri?
Yeah, go ahead.
A lot of the models that we look at, they, how must I say, there's no model life. It's the output of the model that's used to do a prediction for something. It's not always the case, but mostly there's nothing running to do the prediction. For instance, when we say we want to tie a user to a number of articles to propose to him, we have that stored somewhere. That's the output of the model. And then, for instance, a data API can quickly do a key value lookup, or if we want to use it differently, for instance, in an email, we don't do the inference on, it's not real inference, we just do a lookup at that point in time. It's making it easy for ourselves, because otherwise we have to make sure that the model is up and running constantly, and yeah,
No.
it's
So
more
you're not,
difficult.
yeah, so you don't really have models running, let's say. You're not really training them or running them.
Yes and no. On this, in this setup, no, at the moment.
Yeah. And then final question on, do you have also some, say, work done on model visibility to get some insight on actually how the model runs? And is that something that Dask helps you with?
We're doing a POC with NannyML. Shout out to the guys. And they we're setting up the first couple of workshops on it. So what we'll do is we'll take the inputs and the outputs and compare them. Basically, it's very short, but yeah, that's what gets done. So like accuracy, comparing it, etc. It's more involved, but can't also completely say too much about NannyML, I'm guessing. So.
All right, perfect. Now I have to go now, but a really interesting presentation, so thank you.
Interesting questions also. I'd like to discuss this longer. Thanks.
Yeah, maybe I have still one question. So in Spark, it's really easy to, for example, package your codes, set it to Spark submit, and execute it. But yeah, I've played around with Dask, and I don't really see how it works in Dask. So how do you guys do it? How do you package your code, or just the notebook that you run?
So what happens? Joeri, you can also go in if you.
Go ahead.
Okay. So what happens? It builds the graph while you type. Yeah. That's given to the scheduler. So in our setup, and it's not always like that. It's an opinionated setup, but in our setup, there's a notebook, and the notebook spawns a scheduler. And then he says, for instance, if you sum A and B together, and you have C, then he will make the key values and then just tie it to each other. He makes the graph, gives it to the scheduler. The scheduler knows what he needs to compute. So the moment that you ask, give me C, then the scheduler knows what to do. So the scheduler is, in fact, the driver, well, limited functionality of the driver, as I understand it correctly, in Spark. It's not the complete code base. If you say like, I want, for instance, a library, a certain library, then you have to be very careful. Yes, you need to know that it's available on your worker. You can send it. You can have, you can send code to the worker, to a specific worker or whatever, and they can, when they go down and restart, for instance, due to failure, they will automatically re-execute that code. So you could load up your libraries there. We did try that approach, but I don't like it that much, and we make sure that all the workers share the common libraries, including our own. libraries, so that everybody starts from exactly the same setup. There are some, I know a guy that packaged things and automatically sent them to workers, etc. But guessing the times he was on the phone with me, I don't think it was an enjoyable experience.
Okay. So actually, the first thing you do every time is connecting to the scheduler in your script.
Yeah.
You always
So,
connect to the scheduler, and you get, and then from there you start.
yeah. So the process spawns the scheduler, and then there's like this global. It's like automatically. Dask knows when it's in that notebook that it's tied to that specific scheduler. And so there are a number of notebooks on that machine that you're working on your Jupyter Lab, number of schedulers, and they're tied to each other with, let's call it environmental variables.
Okay,
so you don't really, you're constantly asking stuff to the scheduler and giving him information, and you're not writing code, packaging, and then giving it to the driver program.
Okay, I see. All right. I have no further questions on.
All right. Thank you for your time, Joeri and Paul. Thanks everyone for attending. Thanks for the questions. You can find more videos like this on our YouTube channel. Make sure to like the video if you liked this session. Subscribe to the channel. We have a meetup page where we will announce future sessions. This is part of the Data Engineering Guild. Yeah, thanks again to Paul and Joeri for explaining why they chose Dask. It was very interesting to see.
It was a pleasure. It was very nice to be able to once explain it to somebody. So.
Yeah, I can imagine. Yeah. All right, and everyone, I'll see you next time.
Thanks. Bye bye.
Okay. Thank you. Bye.